Okay, so these are going to be our notes over our stretching and shrinking investigations, 3 and 4. Okay, so you need to take out your big idea notebook and get ready to go. All right, so let's start by just writing stretching and shrinking investigation 3 and investigation 4 at the top. All right, so here are the big things we were supposed to get out of these two investigations. So, number one, if two polygons are similar, what is true about their corresponding ratios? So the ratios that correspond. So let's look at a for instance. So let's say I've got this triangle, which is just a three-sided polygon. Okay, and I have this similar, so in this enlargement triangle, another polygon. And let's say that these things are similar. So their angles are the same, their scale factor the same. Oh, goodness, I could have drawn that a little bit better. Okay, so let's say I've got, let's do some numbers here. So let's say this is a length of 3, 5, and 4. Let's say this is 4.5, 7.5, and 6. Okay, so corresponding ratios. So like, let's take this side and this side. So we're going to first write the ratio of those two corresponding sides. So that would be 3 to 4.5. Okay, so just a ratio of the two parts that go together. And let's compare that to, let's take a look at this corresponding side with this corresponding side. Okay, so what's the ratio of that? That's 4 to 6. Okay, and then our last corresponding side. So let's go ahead and take this side right here and this side right here and write that as a ratio. So I'm going to write that as the ratio of 5 to 7.5. Okay, so and what's true about each of these ratios? Okay, so if you have a little bit of a trouble telling if the ratios are the same, a quick way that you could check them is just to go ahead and divide the numerator and denominator and see what happens. So I'm going to do 3 divided by 4.5. I'm just going to convert that ratio to a decimal. And then I'm going to do the same thing as with 4 divided by 6. And I'm going to check that with 5 divided by 7.5. So without either like scaling them up or scaling them down, I could see that if I converted these ratios to a decimal form, basically making it out of 1, that each of these decimals is equal to 0.6 repeating. Okay, so in decimal form. Okay, so I'm noticing that these ratios are each equivalent to each other. So that's just a quick way to tell that those ratios are the same. All right, so what is true about them? We should say that they are equal. Okay, so we compared the corresponding ratios, the ratios of the corresponding sides. All right, second big idea. So sometimes we can look at it this way. So if two polygons are similar, what is true about their, let's call these internal ratios. Okay, internal ratios. All right, so let's go ahead and look at those polygons again. So I'm going to go ahead and remake my triangles. Let's say this side is 3, this is 5, and this is 4. Okay, and let's say I've got this similar triangle, and this is 4.5, 7.5, and 6. Okay, So instead of comparing the corresponding ratios, the ratios of the corresponding sides, I could look at their internal ratios. Okay, so I'm going to look at the ratio of this short side to long side. Okay, and I'm going to compare that ratio to this short side to long side and see what I notice. Okay, so let's look at the ratio of 3 to 5. Is that the same as the ratio of 4.5 to 7.5? Okay, and again, a quick way to check to see if those things are the same is just to do it in decimal form. So, we could either scale them up and scale them down to show that they're the same. Okay, but a quick check is just go decimal form. So I'm going to do 3 divided by 5. Okay, that looks like in decimal form that's 0.6. And how about 4.5 divided by 7.5? Okay, that's 0.6 also. Okay, so both of these are equal to 0.6. All right, so these two ratios are the same. So we could say they are equal. Okay, so corresponding ratios are the same along with internal ratios as long as the two polygons are similar. Okay. All right, let's look at our third big idea. Okay, sorry about that. I was getting some glare on my paper. So, all right, so third big idea is describe two ways to find a missing side in a pair of similar figures. Okay, all right, so let's say I've got these two similar figures. So let's say I've got this figure and this side is, all right, let's say this is 5, this is 12, and this is 13. Okay, and let's say I've got the enlargement of it. Okay, and it's similar. And this side is 8 and this side is x. How can I figure out what x is? Okay, so there's really kind of two strategies that we've used. Okay, so the kind of first strategy is to use scale factor. Okay, so in a class we kind of called that Jude's method. Okay, so how do I find the scale factor? So all I'm going to do is look at the two sides that I see going together, so 5 and 8, and I'm going to find the scale factor. So how many times that is multiplied to get that one, okay? So I'm going to take 8 divided by 5 to figure out how many times bigger 8 than 5, okay? So then I find out that that's 1.6. So I know that this triangle has been scaled up by a factor of 1.6. So once I have that, then I'm going to multiply the scale factor by the side that corresponds to the missing side. Okay, so my missing side was x. What side corresponds with that? Looks like 13. So I'm just going to use that scale factor of 1.6 and multiply that up. So I'm going to take 13 times 1.6, and then I get 20.8. So my length of x right here would just be 20.8. So I just scaled it up, figured out that scale factor. Okay. Now remember, if you're trying to find a shorter side, make sure your scale factor is less than 1, so it might actually shrink. Okay, so the other way we could do this is we could use ratios. And set up a proportion. Okay, So, and we can either use internal ratios or corresponding ratios, okay? So let's try and first do the corresponding ratios, okay? So if I look at my numbers again, okay, it looks like 5 and 8 are the corresponding ones. So 5 corresponds to 8. So we're going to write the ratio of short side to short side. And I'm missing these. So I'm going to write the ratio of 13 to x. So those ratios should stay the same. Okay, my corresponding ratios. Okay, just like from the previous notes that we saw. So all I'm going to have to do is figure out what x is. Okay, now this isn't a super easy, when we're thinking about equivalent fractions. So it'd be nice if that was a 10 because that would kind of do, scale up nicely. So, but it's a 13. So sometimes you have to do a little figuring. So what turns a 5 into a 13? So let's think about our fact families. Okay, so instead of just guessing, I could go ahead and do 13 and divide it by 5. Okay, so I'd be multiplying by 2.6. All right, so I'm just going to scale this by 2.6 and then do the same to the bottom by 2.6. All right, so I could scale that up that way. So let's see, if I take 8 times 2.6, okay, it looks like by those ratios that have to be 20.8, just like what we thought earlier, okay? Or sometimes the easier ratio is an internal ratio. So maybe I'll use my internal ratios and just do this ratio compared to this ratio and see if those match up. So I'm going to write down the ratio of 5 to 13. How does that compare to 8 to x? Okay. Okay, so, and again, I've got to think a little bit, so it's not like it's just times 2. So I'm going to have to take 8 and divide it by 5 to figure out my multiplier. So it looks like it's times 1.6 and then times 1.6. So I could also just do those internal ratios and find that missing part. So I could take 13 times 1.6 and see that it's 20.8, just like with the other method. Okay, so scale factors or ratios. All right, so, and then the last thing that couple classes got to is, and you saw some in the videos, okay? So I know a couple of classes got outside and we tried to at least talk about how we do the shadow method, except for unfortunately it was kind of cold and rainy. And then, but we did do the mirror methods with a couple of classes. So let's see how we could actually apply some of this stuff. So fourth big idea was how can you estimate heights. Oops, heights, goodness. And distances you can't easily measure with rulers or tape measures. Okay, so we went outside. There's a couple of classes, and we tried to see how high the goalpost was. Okay, and it wouldn't have been really safe to have somebody like climb up to that tip top of the goalpost, was it? So what we did is we couldn't use the shadow method because it was cold and rainy, but we did use a mirror method. So we got kind of two different methods. We could maybe use shadows or mirrors. So although we couldn't use the shadow, we talked about it. Okay, so we could have gone back outside and like, oh, maybe let's if we had a flagpole outside. So let's say how we could use shadows and similar triangles. Oh, look at that sunshine popping in now, right on my stuff. If we would have been able to do it today. All right, so let's say we went outside and we looked at the flagpole. Okay, so, and we're not going to shimmy up to the top. Let's say we wanted to find that height of that flagpole. Well, one thing we could measure is if it had a nice long shadow out here, we could go ahead and measure the shadow for that flagpole. Okay, So let's say that that shadow ended up being um, like 15 feet or something. Okay, how about that? Okay. All right. And then let's say that we had somebody standing outside. Mhm. And we could probably measure that height, couldn't we? Okay, so we measured the shadow. Okay, and then we measured the height of this person or other object that we could even use. Okay, let's say that that person was 5 feet tall. Okay, and then let's say that the 5 foot person's shadow was, say, maybe 3 feet. Okay, so 3 feet. Gosh, I probably drew this a little bit long then if I wanted to keep it similar. Well, we talked about how the sun was so far away that if the shadow that's being cast basically makes two similar triangles. So if we wanted to find this, all we have to do is use some of those techniques from number 3 and figure out how tall that is. Okay, so we could either use scale factors or we could use ratios. I think I'm going to do scale factors. So what's the scale factors? How many times longer was this shadow than that person's shadow? So I'm going to go ahead and take 15 and divide it by 3. And I'm going to get 5. Okay, so 5 is our scale factor. Okay. All right, so then I'm going to take that and scale this up. Okay, his height by that same. So I did times 5 here. So I can do times 5 here. So I'm going to scale that up by 5. So I'm going to go ahead and take his height and multiply by 5. And now I figured out my missing x. So 25 would be the height of the flagpole. Okay, so I'm so bummed it wasn't sunny enough for us to actually do that. Okay. All right. So the second way, so we did actually try this with a couple of classes. We could use a mirror and similar triangles. Okay, so let's say we still have that flagpole. Okay. And we placed a mirror on the ground. This is our mirror. Okay. So, and again, we're trying to find this height of this flagpole. It's, we don't want to shimmy up to the top. But let's say we have this person standing here, just kind of having a peek. And they're standing at a point where when they look in this mirror, okay, they can see the top of that flagpole. Okay. So I guess I should have drawn this a little bit better, but this angle of reflection ends up being the same. Okay, so again, we've got two similar triangles again. We could measure this without getting ourselves into trouble. So we'd be shimmering up here. It's on the ground. And let's say this is 12.5 feet. Okay. And then we can measure this without too much trouble. Let's say maybe that's just 2 feet. Okay. And let's say our little brother's doing this. This is just maybe 4 feet is the height. Okay. So we got 4 feet as the height to this person's eyes. They're 2 feet away from the mirror. And then the mirror had to be placed, it was 12.5 feet away until they got that measure. Okay, so again, we could use either internal ratios or we could use scale factor. So whatever you want to use, I'm saying, oh, this internal ratio might be kind of nice. So I'm just noticing that this ratio is like 2 to 1. So the same thing's going to happen over here. So if I write ratio of 2 to 4, okay, so 2 to 4, that should be the same ratio as 12.5 to x. Okay. Goodness, 12.5. Okay, so 2 to 4, what would that have to be? So I'm just noticing the denominator's double, so it looks like our height would have to be 25 feet. Okay, so in that is how we could use a mirror and similar triangles to find the height of something that we can't do directly.